on this last page here, we're going to make a quick attempt to explain exactly where it is that these subshells are and kind of what they look like. And so it's a little bit abstract, but we can try it. So let's start with a subshell and the maximum number of electrons that will fit in that subshell just by the width of that section on the periodic table, right? So the S can hold up to how many? 2. The P can hold up to 6. D can hold. F can hold 14. Okay. So it turns out we talked just very briefly about orbitals before. An orbital is a volume where you're likely to find an electron. It's just a place where an electron is. Okay? And that electron is zooming around, but it's spending most of its time inside this particular volume. Okay? An S subshell, even though it can hold 2 electrons, every S subshell is made of just one orbital. Okay? So that one orbital can hold 2 electrons. So these pictures that I have here, right to the side of that diagram here, are pictures of a couple of S orbitals. It looks kind of funky up there, but this is a 1s, and to approximate scale, that would be a 2s. Okay? And so really what that is if we had 1s2, 2s2, 1s2 would be just 2 electrons within here, okay? And then 2s, because we're in the next shell, that's occupying a bigger space, and we have 2 electrons somewhere within this space, and they overlap. Okay? So it's just that the 2s electrons are occupying a larger space that's sort of on top of where the 1s electrons were. Okay? So you could sort of imagine that maybe the 1s is inside of here somewhere, like that. Okay? So it doesn't matter. They're sort of overlapping the same space. But for any 1 electron, that's what we're talking about. So 1s2, 2s2 looks like 2 electrons in here, and then 2 electrons in here. That's really all that looks like. Okay? And that's what all the s orbitals are. That's really very simple. S orbitals are spherical. I don't know if it's just a coincidence that s's are spherical, but that's what shape they are. Okay? So it turns out that if an s subshell contains a single orbital, right, one orbital that could hold 2 electrons, if that same thing held true, that one orbital can hold 2 electrons, how many orbitals do you suppose there are in a p subshell? Yeah, there are 3 orbitals. Okay? So there are 5 orbitals in a d subshell and 7 orbitals in an f subshell. And that's because every orbital can hold a maximum of how many electrons? 2. Okay? So let me show you this other picture right here. This group would be like a 2p subshell. Okay. S orbitals are spherical, like a basketball, okay? But a p orbital looks like this. Okay? This right here is a p orbital. And this is another, and that's another. Okay? So every p orbital has sort of 2 lobes to it, like that, meaning that the electron lives somewhere within this space. So you could have an electron over here, but probably not right in the middle where the nucleus is. Okay? Different from S subshells, which are sort of centered around the nucleus. And it gets less likely the further you get out. Okay? P orbitals have what's called a node in the center, which is just a place where there's no electron density. So remember I was talking a bit about waves and particles, I said very briefly that both electrons and light actually have wave-like properties and particle-like properties. Well, the shapes of these orbitals come from electrons' wave-like properties. Because if you imagined, and I always threaten to bring one and I never remember, but say you had a jump rope tied to the wall over there. We'll use our imaginations. And if you go up and down like that, you can make a big up and down, sort of like that, right? Just like a regular jump rope would, okay? Like a jumping rope. But if I start going faster, I can get it where one side is going up and the other side is going down, right? But there's really nothing in between. You're going like this for a while, and then you start finally getting fast enough, and then you've got that, okay? So that's sort of like a wave-like property. If an electron is behaving like a wave, once that electron gets enough energy, it can start doing, that, as opposed to just going up and down. See how that works? So the reason there are 3 of them is because that's the only way we can make a symmetrical shape out of something with 2 lobes like that. Okay? We can have one of them sort of going in the x-axis and one of them going in the, the y-axis or the z-axis, but you've got your 3 axes of your coordinate plane system, right? So the x and the y and the z, right? Up, down, left, right, front, back. So all 3 of these orbitals are overlapping. Okay? You've got one of them that's going this way. On the very same place, you've got one of them going that way, and you've got one of them going that way. Okay? So the reason a p subshell is full with 6 electrons is because if we have 6 electrons, then we've got that one full, and that one full, and that one full. And now it's symmetrical. Okay? See how that works? So we can hold up to 6 electrons, okay? Up to 2 in each of those, and we'll talk about the order that they go in, but that's how p subshells work. Okay? So where s were spherical, 1 spherical, p's have 2 lobes. I'll say 2-lobed shape. Okay. And it becomes more complicated as we increase the number of orbitals in a subshell. Okay. In the d subshell, there are actually 5 of them. 4 of them are sort of look like clover leaves. Right? They sort of look like clover leaves in 4 different directions, and then there's one of them that's sort of different to balance out the symmetry of it. It's kind of interesting. And then the f orbitals get even more complicated looking. They sort of look like blooming flowers. They've got all kinds of little lobes to them. So you should know what s and p orbitals look like, because that's simple. And you should know that as we continue on, they get more complicated. But all of these shapes are sort of superimposed within the same place. An increasing shell increases the overall size of these things. Okay? But that's sort of how it goes from that point. Okay? So we can then start to think about what it looks like for these for how electrons are filling into these orbitals, and we can use an orbital diagram for that. There's a couple of ways to do this. Let's just start with an O. Okay, O's electron configuration is 1s2, 2s2, then what? 2p4. Okay, so here, let's just write that right here. 1s2, 2s2, 2p4. Okay? One way to indicate that would be making a box for each orbital. Okay? There's a box. And then those 2 electrons, I'm going to make an up arrow and a down arrow. Okay? The box is an orbital. The arrows are electrons, valence electrons. No, just regular electrons, not necessarily valence. Okay? The reason that 2 electrons can fit into one orbital is because of a property called spin. You can sort of think of it kind of like the direction that the electrons are going, although it's not quite like that. But every electron fundamentally will either have what's called an upspin or a downspin. Okay? And the only way two electrons can fit into the same orbital is if they have opposite spins. Two electrons with the same spin will repel each other, so they can't fit in the same place. So 2s2 would look very similar. Let's draw a box. Up arrow, down arrow. Okay? So now that we have 2p, how many boxes should I draw? How many orbitals would be in any p subshell? 2? There are 3 orbitals, right? The left, right, the front, back, and the up, down. Okay? Those are the 3 orbitals. Whether or not they're full, that's a different question, but there are 3 orbitals. What I'm going to do, I'm going to draw 3 boxes that are attached, like that. Okay? This is another way of thinking of the 2p subshell. Okay? And those electrons are going to go into that subshell in a way that spreads them out the most. So if I've got 4 electrons, I'm going to put one here. Okay? But if we're spreading out as much as possible, where do you suppose the next one will go? Okay? They're actually going to go one at a time, like that. And they're going to go individually first into orbitals. Okay? They're going to fill orbitals singly first, put 1 electron first. And then, only after each orbital has 1 electron, then we can start pairing them up. Okay? So that's what 4 electrons would look like in a p subshell. Okay? 3 electrons would look like just each orbital has 1 electron. Okay? 4, they would have to start pairing up. Okay? So think of it like a camp cabin or something like that has 3 bunk beds. Okay? And if you get 4 kids, the first 3 that get in there are claiming their own, and then the 4th one has to pair up. So think of it that way. So that's one way of thinking of it. A very similar idea would be showing those subshells, but sort of stacked up. You'll see this in mastering chemistry, where 1s would look like that, and it actually draws the arrows sort of on the line. And 2s looks like that. Okay, but 2p would look like that. So you could sort of think of that like increasing energy. 1, oops, red. There. So that's just another way of drawing 1s2, 2s2, 2p4, like that. Okay. Pretty much means the same thing, just a slightly different way that they're drawn. Okay? So in a certain kind of question in mastering chemistry, it has you build the electron configurations, sort of like that. So you would click on the little 1s, and that puts that there, and you would click in there to put its arrows in. And then you click on 2s, that makes that one, you put its arrows in. Click on 2p, that makes these ones, and you click in the boxes to insert the arrows in there. Okay? So you're sort of building up the electron configuration as you go. Okay? So let's look at what happens when we have O2 minus. That's an ion, right? Because it has a charge to it. What would have to happen to O in order for it to become O2 minus? What does O need to do? Gain what? It needs to gain 2 electrons. Let's write that right here. If we gain 2 electrons, okay, if we draw those same boxes or the same orbitals, it'll still be 1s2, It'll still be 1s2, 2s2. We started with 2p4, 1, 2, 3, 4. You just told me we needed to gain 2 electrons. Can you see why it would be so favorable for oxygen to gain 2 electrons? What does that do to the oxygen? It fills up the rest of those spots, right? We got one there. Let's make it orange like my writing. One there, one there. So the electron configuration for O2 minus would be 1s2, 2s2, 2p6. Okay. What other atom on the periodic table has the configuration 1s2, 2s2, 2p6? See? And neon is a what? Noble gas, which means it is stable. If I've taught you anything about noble gases. Okay. O2 minus has the same electron configuration as neon. Which makes it stable. And now we have a reason for that stability. Think of the shape of those p orbitals. Okay? One is left, right, one is front, back, one is up, down. When we have 6 electrons occupying it, we have all of those orbitals full. And it's nice and symmetrical and balanced and in a good position. Okay? So that's why an O that's alone will try everything it can to gain 2 more electrons from somewhere so that it can be stable and symmetrical, just like neon. Let's do the same thing with sodium. 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. And then what for sodium? 3s1 right here. Okay, so I'm not going to draw all those out, but I will draw this one here. I'll draw the 3s1. Okay. These ones in here are all full. Okay. Why do you suppose sodium likes to become an A+? Likes to get rid of that one extra electron, right? If we lose, then we're down to, right? If we lose this one right here, we're down to 1s2, 2s2, 2p6, right? 1s2, 2s2, 2p1, 2, 3, 4, 5, 6. What's so special about this set of electrons? Does it look familiar from 2 lines up? It's a stable. Okay. So when we form what's called a stable ion, right? O2 minus is a stable ion, F minus, Na plus, oops. Magnesium, what's its charge? 2 plus. All of those have neon's electron configuration. Okay? They all do that because they're stable. And we could do the same thing again on the next row. S2 minus, Cl minus, K plus, Ca2 plus. Those all have argon's electron configuration. Okay? So we end up with this sort of bunch of stable ions on either side of a noble gas that have that noble gas's same electron arrangement. Okay? So when you're asked whether or not an ion is a stable ion, okay, it's that kind of question. Okay? Have we gained or removed the correct number of electrons for it to be a for it to be similar to a noble gas. Now, transition metals, they do something different, and that's sort of beyond the scope of this class. But that has to do with the fact that transition metals make variable charge ions. Okay? There's not just one exact way to make the most stable transition metal ion. There's lots of ways. Okay? But these ones right here that are just sort of on either side of a noble gas have a predictable way of forming stable ions just by mimicking the electron configuration of the noble gas that it's nearby. That make sense? So there is a practice worksheet for electron configurations that has you write electron configurations for atoms as well as ions. So if you're ever writing the electron configuration for an ion, add electrons for a minus or remove electrons for a plus. Okay? And then based on sort of that number, you can tell whether it's stable or not. So anybody have questions about that? That look good?